The revelation of a 0.9-meter gap in the Tesla Model 2's chassis caught many by surprise, and for good reason. This unusual gap in a production car immediately raised questions about structural safety, durability, and design integrity. Elon Musk himself publicly confirmed this detail, leaving no room for speculation. It's an intentional and strategic choice. Instead of hiding it, Tesla decided to highlight it. The burning question is simple. Why would a new generation electric car have a nearly 1-meter hole in the middle of its structure? What at first glance appears to be a flaw is actually the heart of an industrial revolution. To understand what's behind this, we need to look at how cars have always been manufactured. The traditional model uses hundreds of pressed metal parts, joined by thousands of spot welds. In a typical sedan alone, there are approximately 400 different components in the chassis, connected by up to 1/600 spot welds. Sounds robust? In theory, yes, but each weld is a potential point of failure, with risks that multiply in collision situations. This structural complexity, besides being costly, is vulnerable. It's like building a castle with glued pieces. With each new spot, the chance of something coming loose under pressure increases. What Tesla did was radical. It threw out that playbook and turned to so-called mega foundries, or mega castings. Instead of hundreds of small parts, the company began casting giant car parts from a single piece of aluminum, using presses weighing up to 9,000 tons. The process transforms the car's structure into something more like a single-piece mold than a welded jigsaw puzzle. This method had already been used on the rear and front ends of other models, but with the Model 2, Tesla took it a step further, and that's where the 0.9-meter gap comes in. This space is located precisely between the two massive castings, the front and rear. Instead of connecting these sections with welds or other small metal parts, Tesla uses the battery pack itself as a structural link. The gap, therefore, isn't a literal void. It represents the critical joining zone, where the two aluminum blocks are connected by a third, ultra-rigid element, the battery pack. It's as if the car's floor were a continuous beam, absorbing and distributing forces more efficiently than any spot weld could. This strategy was designed to reduce weight, increase strength, and cut production costs, and of course, pave the way for a new era of cheaper vehicles. After all, fusing two giant parts is much faster than welding 1,600 points. This means less assembly time, less labor, and less margin for error. The savings achieved at this stage are one of the keys to the Model 2 achieving an estimated price below $25,000. It's not just a futuristic design, but an economic engineering move that aims to turn the market upside down. But why has the gap generated so much controversy if the concept is so advanced? The answer lies in perception. For those accustomed to continuous structures reinforced by multiple connections, a physical space between two sections may seem fragile. It's counterintuitive to imagine that something more empty is also stronger. This is especially true in an industry as conservative as the automotive industry, where structural innovations often take years to gain acceptance, even when they prove superior in practice. As a result, the first comments on social media were suspicious. Images showing the gap between the parts began to circulate with alarmist captions, and mainstream experts questioned the choice. There were fears that the car could split in half in a head-on collision. Some even called the Model 2 a stitched car. But, as Musk himself stated, this isn't stitching, it's integration. And every detail of this joint was designed to withstand stresses that would destroy a conventional car. The choice of mega castings over traditional welding wasn't just to impress with cutting-edge technology. It solves long-standing problems that many consumers didn't even know existed. Every weld is a potential failure point, but it's also an area that consumes time, energy, and money to execute. Producing a car conventionally requires 2 to 3 hours of extra time just to weld all these parts, which increases the cost of each unit by up to $1,000. Ultimately, the buyer pays for this outdated process without realizing it. Tesla understood that if it wanted to offer a truly affordable electric car, it needed to reinvent the assembly line. The beauty of megacasting lies precisely in the brutal simplicity of the idea, reducing hundreds of parts to 2 or 3. This not only eliminates weak points, but also drastically shortens production time. With the colossal presses Tesla uses, it's possible to mold the front or rear of the car in less than 10 minutes. Compared to the traditional method, this represents a leap in efficiency of more than 30 times. Furthermore, each part comes out virtually ready-made, with few adjustments required, and fits perfectly into the assembly points. This also reduces human error and the need for constant inspections. But the impact isn't just on speed. With fewer components, the car also weighs less. The Model 2, with its reconfigured structure, managed to reduce the weight of the lower chassis by 27%. This means better road performance, longer battery life, and less wear on components like brakes and suspension. And here's a detail few notice. Less weight also means less mass being displaced in an emergency braking or collision, which can be the difference between a scare and a tragedy. This weight savings, combined with the robustness of the single casting, has enabled something almost unthinkable just a few years ago. A Tesla for under $25,000. And this isn't just marketing hype. The math behind this reduction is real and revolves around a very simple concept: cutting out everything superfluous or inefficient in the manufacturing process. With a structure that eliminates hundreds of small parts and thousands of welds, labor, material, and rework costs drop dramatically. And the lower the factory costs, the more affordable the car becomes for those at the cutting edge. This paradigm shift also creates a new benchmark for the automotive industry. Traditional automakers, operating with tight margins and outdated processes, are now being forced to observe what once seemed like futuristic experiments like Tesla. Megacasting has become a trend, and there are already rumors that other brands are trying to copy the technique, even without yet having the technology or infrastructure to do so. What was once an eccentricity is now a real threat to the way cars have been built for over a century. And speaking of threats, it's worth remembering that the Model 2's 0.9-meter space isn't just a physical union of parts, but rather a seam of ideas. This is where the front and rear castings meet, acting as the structural floor. This junction was designed to withstand forces that would destroy a traditional welded chassis. Instead of hundreds of small connections, there are 3 main connections, each engineered to be extremely strong. It's a complete shift in philosophy. Fewer points, more strength, more control. The decision to rely so heavily on the battery as a structural component may seem bold, but it was tested, calculated, and optimized at every level. Tesla didn't just redesign the car, it redesigned the logic of vehicle construction. Every gram lost, every second saved on the production line, and every screw eliminated has a direct impact on the final product. And consumers are beginning to feel this impact now when they look at the price, see the performance, and understand that behind that clean, seemingly simple design lies one of the most ambitious engineering processes in recent history. If the automotive industry was once moving toward an electric future, now it's racing. And with the Model 2, racing faster than ever. Because the goal isn't just to electrify cars, it's to make them viable, affordable, and safe enough for anyone to own. And it all starts right there, in that 0.9-meter space that generated so much amazement. It's physical proof that cutting out the excess doesn't mean losing safety. On the contrary, sometimes it's precisely in the void that true strength lies. The real distinguishing feature of this design lies in the connection between these 3 parts, front, rear, and battery pack, that form the structural heart of the Model 2. And here, Tesla abandoned any notion of conventional methods. Instead of welding, which creates weak points and poorly distributes stress, the company chose to bond these gigantic parts with structural adhesives used in the aerospace industry. That's right, the same type of material that holds entire airplane fuselages together at 33,000 feet is now supporting the chassis of a $25,000 car. It doesn't look real, but it is. The strength of these bonds is impressive. Each joint is secured with high-strength bolts, rated up to 1,200 MPa, pressing the parts together with a force equivalent to 30,000 pounds. It's as if two blocks of aluminum were crushed together until they become virtually inseparable. The contact surface between these parts reaches 2.7 square meters, compared to the tiny 2 linear millimeters achieved by traditional welding. In other words, instead of small seams that withstand impact at isolated points, Tesla created a large, uniform connection capable of distributing force much more efficiently. These details aren't just engineering theory. They've been tested, measured, and proven. The Model 2's new chassis has achieved 30% greater torsional rigidity than the Model 3, with 20% less structural weight. This means the car is more resistant to twisting during fast cornering or side impacts. At the same time, the extra lightness increases battery range and improves stability, as less mass is shifted during quick maneuvers. The steering feel also changes, and for the better. The car handles like a solid block, even though it's modularly assembled. This additional rigidity also directly impacts crash safety. In severe collisions, the goal is not only to prevent the car from deforming, but to ensure that the cabin remains intact. And that's exactly what the new structure provides. In simulations and real-world tests, the Model 2 has been shown to absorb up to 25% more energy than its predecessor, the Model 3. At the same time, cabin intrusion, the extent to which the structure invades the driver and passenger space, has been reduced by 15%. These figures aren't just better. They redefine what's expected of a passenger car in terms of protection. Another interesting fact, the engineers achieved this feat with fewer components. The new chassis weighs about 180 compared to 225 kilos for the previous steel version. This 45-kilo reduction in structural mass equates to less inertial load during cornering, less wear on tires and brakes, and overall lighter driving dynamics. It may seem small, but in a car, every kilo counts, especially when the goal is to increase electric range without needing a larger and more expensive battery. And that's where everything starts to fit together. Weight, cost, time, and safety are directly connected in this new model. It's impossible to ignore the leap in efficiency this represents on the assembly line. A traditional chassis, made with stamping and welding, takes about 6 hours to complete, requiring frequent inspection and rework. In Tesla's new process, each section can be cast in 10 minutes. Combine this with simplified assembly and reduced need for inspection and correction, and the result is 36 times greater productivity. This completely changes the scale of production for a popular electric car, something that, until now, was only possible with much more expensive vehicles. This efficiency translates directly into market power. Because, while competitors are still struggling to manufacture EVs for under $30,000, Tesla is already projecting profits on $25,000 models. And not only that, it delivers a safer, lighter product with superior structural performance. And all of this revolves around a bold choice, creating a chassis with only 3 critical connections, with a 0.9-meter gap between them. A space that seems daunting at first glance, but in practice represents one of the strongest joints ever seen in a civilian car. While many are still trying to understand how this solution is possible, Tesla is already applying it at scale, not as a prototype, but as a real model that should hit the streets soon. And perhaps this is the most intriguing detail of all. What seems strange today, a structure with a void in the middle, could be the new industry standard tomorrow. Because if something as simple as eliminating welds can make a car cheaper and safer at the same time, the question remains, why hasn't anyone done it before? A direct comparison with traditional welding reveals a paradigm shift that's hard to ignore. For decades, the automotive industry relied on the idea that the more welds, the safer the car, a belief based on redundancy. But what Tesla engineers discovered is that too many weak connections can be more dangerous than too few strong ones. And that's precisely what motivated the creation of this structure with 3 ultra-reinforced key points. Instead of relying on hundreds of joints, the company bet everything on fewer, but much more robust, points. This concept was evident in the choice of materials. The aluminum alloy used in the Model 2 isn't just any conventional automotive aluminum. It's a proprietary Tesla formula, with a tensile strength between 140 and 175 megapascals compared to the industry's typical 90 to 120 MPa. In practice, this represents a structure 40% stronger than the current standard, a transformation that completely changes how the car responds to shocks, pressure, and wear over time. Most impressively, this alloy also offers high electrical conductivity, contributing to the vehicle's overall efficiency. But it's not just the material that matters. How it's joined makes all the difference. Tesla's structured bonding system uses adhesives with a shear strength of 30 MPa, the same ones used in commercial aviation. When combined with ultra-high-strength screws, these adhesives create a bond that not only matches the strength of the material, but in many cases exceeds it. This means that, under extreme stress, the aluminum part tends to give way before the joint breaks. It's as if the weakest link in the chain ceases to be the link and becomes the rest of the chain. A detail that often goes unnoticed, but is crucial to this new design, is the force distribution area. While a traditional weld concentrates on 2 mm per wide fillets, Tesla distributes the force across a 2.7 square meter surface. This represents more than 1,000 times more area supporting the loads, which completely changes the dynamics of a crash. Instead of concentrating the impact on a tiny point, the force is spread across a large surface, preventing localized breakage and reducing the risk of serious deformation. Test data confirms all of this. The Model 2 achieved torsional rigidity of 35,000 Newton-meters per degree, higher than the Model 3's 26,000. In simple terms, this means the car twists less, even under intense forces. This extra rigidity protects the cabin, improves handling, and reinforces the feeling of solidity during daily use. At the same time, the gain didn't come with an increase in weight. Quite the opposite. The structure is lighter, more efficient, and easier to manufacture. It's the kind of advancement that, when implemented well, doesn't create a trade-off between performance and cost. It improves both. Another point worth noting is modularity. With only 3 large structural blocks, maintenance becomes more predictable and, interestingly, simpler. In the event of severe damage, such as in a collision, it's possible to replace one of these large sections without having to disassemble the entire car. This drastically reduces repair costs and downtime. What's more, because the joints are designed to be accessible and durable, Tesla's specialized workshops can perform repairs with specialized aluminum welding equipment, avoiding lengthy rebuilding processes. For the consumer, this means fewer after-sales headaches. Fewer points of failure result in less corrective maintenance, fewer shop visits, and a longer lifespan for the vehicle's structure.